Grounding the neutral at the surface provides a low impedance path for lightning energy to flow to ground, protecting the surface from lightning or lightning-induced voltage or current. This low impedance path helps to prevent the lightning energy from damaging surface equipment or other parts of the electrical system. When lightning strikes occur, they can induce surges on power lines. These surges can then induce further surges on the transformer and consequently into the house. Grounding the neutral at the surface plays a critical role in mitigating damage from these surges by offering a dedicated path for the surge energy to dissipate safely into the ground. The grounding of the neutral at the surface is also crucial for fault clearing. In the event of a fault on a phase conductor, the neutral conductor acts as a pathway for the fault current to flow to ground. This process facilitates the clearing of the faults, minimizing the risk of damage to the electrical system. Even with proper grounding and no potential difference between grounded non-current carrying parts, lightning strikes can still inflict damage. Lightning can induce very high voltages on the phase conductors. These high voltages can overwhelm and damage electrical equipment despite the grounding measures in place. Installing a lightning protection system is the most effective strategy to safeguard against lightning damage. This system consists of conductors installed in the building's exterior, connected to the ground, providing a direct and safe route for lightning energy to dissipate. Grounding ensures safety. Here's a more detailed explanation of the concepts involved. Firstly, let's consider grounding and bonding. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding connects the electrical system to the earth, providing a reference point for voltage. Bonding connects non-current carrying metal parts to create a low impedance path for fault current. Grounding the neutral at the service entrance establishes a stable reference point for the electrical system's voltage relative to the earth. This is typically achieved by connecting the neutral conductor to a grounding electrode system such as a ground rod or a metallic water pipe that is in direct contact with the earth for at least 10 feet. This connection ensures that the neutral conductor is at or near earth potential, preventing voltage fluctuations and providing a stable reference for the system. Bonding, on the other hand, involves connecting all non-current carrying metal parts of the electrical system together, such as metal enclosures, conduits, and equipment grounding conductors. This creates a low impedance path for fault current to flow back to the source in the event of a ground fault. By bonding these metal parts together, the potential difference between them is minimized, reducing the risk of electric shock. Secondly, the role of low impedance path is also important. The low impedance path provided by grounding and bonding is crucial for both lightning protection and fault clearing. In the event of a lightning strike, the surge of energy seeks the path of least resistance to ground. By grounding the neutral and bonding all metal parts together, a low impedance path is created, allowing the lightning energy to flow safely to ground without causing damage to the electrical system or posing a risk of electric shock. Similarly, in the event of a ground fault, the low impedance path provided by bonding allows fault current to flow quickly back to the source, tripping the circuit breaker or fuse and interrupting the flow of electricity. This rapid interruption of the fault current minimizes the risk of electric shock and prevents damage to equipment. Thirdly, the surge voltage and current are important concepts. Lightning strikes can induce significant surge voltages and currents in electrical systems. These surges can damage equipment, cause fires, and pose a risk of electric shock. Grounding and bonding help to mitigate the effects of these surges by providing a path for the surge energy to flow to ground. However, it's important to note that grounding and bonding alone may not be sufficient to protect against all lightning strikes. In areas with frequent lightning activity, additional surge protection devices, such as surge arresters, may be necessary to provide comprehensive protection. Fourthly, lightning protection systems. A lightning protection system is designed to protect a building and its occupants from the harmful effects of lightning strikes. These systems typically consist of air terminals, conductors, and grounding electrodes. Air terminals are installed on the roof of the building and are designed to intercept lightning strikes. The conductors then carry the lightning current safely to ground, where it is dissipated through the grounding electrodes. Lightning protection systems are designed to provide a low impedance path for lightning current to flow to ground, minimizing the risk of damage to the building and its contents. They also help to protect against side flashes, which can occur when lightning jumps from one object to another. The National Fire Protection Association, or NFPA, Standard 780 provides detailed requirements for the installation of lightning protection systems. Fifthly, equipotential bonding. Equipotential bonding is the practice of connecting all metal parts of an electrical system together to create a common electrical potential. This helps to prevent voltage differences between metal parts, which can reduce the risk of electric shock. Equipotential bonding is particularly important in areas where people may come into contact with metal parts, such as bathrooms, kitchens, and swimming pools. By bonding all metal parts together, the potential difference between them is minimized, reducing the risk of electric shock. Sixthly, the NEC requirements. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding of electrical systems. These requirements are designed to ensure the safety of people and property. The NEC requires that all electrical systems be grounded and bonded in accordance with specific requirements. These requirements vary depending on the type of system, the voltage, and the location. The NEC also specifies the types of grounding electrodes that are permitted, as well as the size and type of conductors that must be used for grounding and bonding. Seventhly, the ground resistance is also an important factor. The resistance of the grounding electrode system is an important factor in determining the effectiveness of grounding. A low-resistance grounding electrode system provides a better path for fault current to flow to ground, reducing the risk of electric shock and damage to equipment. The NEC requires that the resistance of the grounding electrode system be no more than 25 ohms. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. Eighthly, the surge protective devices, or SPDs, are also important. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. These devices are installed in electrical panels and at equipment locations to divert surge current to ground. SPD are available in a variety of types and sizes to protect against different types of surges. They are typically rated by the surge current capacity, which is the maximum amount of current that they can safely divert to ground. SPD are an important part of a comprehensive lightning protection system. Ninthly, maintenance and inspection are also important considerations. Regular maintenance and inspection of grounding and bonding systems are essential to ensure their continued effectiveness. Grounding electrodes should be inspected periodically for corrosion and damage. Bonding connections should be checked for tightness and corrosion. Surge protective devices should be tested to ensure that they are functioning properly. Any problems that are identified should be corrected promptly. Tenthly, the importance of professional installation and inspection. Grounding and bonding are critical aspects of electrical safety. It's important to have a qualified electrician install and inspect your grounding and bonding system to ensure that it meets all applicable requirements. A qualified electrician will have the knowledge and experience to properly design and install a grounding and bonding system that will protect your home and family from the hazards of electricity. Now let's consider some specific scenarios and how grounding and bonding work to protect against lightning and other electrical faults. Firstly, a direct lightning strike. In the event of a direct lightning strike to a building, the lightning current will follow the path of least resistance to ground. If the building is equipped with a lightning protection system, the air terminals will intercept the lightning strike and the conductors will carry the current safely to ground. If the building does not have a lightning protection system, the lightning current may enter the building through the electrical system, plumbing, or other metallic objects. In this case, the grounding and bonding system will help to divert the current to ground, minimizing the risk of damage to the building and its contents. Secondly, an indirect lightning strike is another important consideration. Even if a building is not directly struck by lightning, it can still be affected by indirect lightning strikes. These strikes can induce voltage surges in power lines, which can then travel into the building's electrical system. Grounding and bonding help to protect against these surges by providing a path for the surge current to flow to ground. Surge protective devices can also be used to protect against these surges. Thirdly, a ground fault. A ground fault occurs when a live wire comes into contact with a grounded metal object. This can happen if the insulation on a wire is damaged or if a wire comes loose and touches a metal enclosure. Grounding and bonding help to protect against ground faults by providing a lower impedance path for the fault current to flow back to the source. This causes the circuit breaker or fuse to trip, interrupting the flow of electricity and preventing electric shock. Fourthly, static electricity can also be a problem. Static electricity can build up on objects, particularly in dry environments. When a person touches an object with a static charge, they may experience an electric shock. Grounding and bonding help to prevent the build-up of static electricity by providing a path for the charge to dissipate to ground. Fifthly, voltage fluctuations can also occur. Voltage fluctuations can occur due to a variety of factors, such as changes in the load on the electrical system or problems with the power supply. Grounding helps to stabilize the voltage by providing a reference point for the system. This can help to prevent damage to equipment and ensure that the electrical system operates properly. Let's delve into some practical examples. Consider a residential home. In a typical residential home, the neutral conductor is grounded at the service entrance. This is usually accomplished by connecting the neutral conductor to a ground rod that is driven into the earth. All metal parts of the electrical system, such as metal enclosures, conduits, and equipment grounding conductors, are bonded together to create a low impedance path for fault current. Surge protective devices are often installed in the electrical panel to protect against voltage surges. Now consider a commercial building. In a commercial building, the grounding and bonding requirements are generally more stringent than in a residential home. This is because commercial buildings typically have more complex electrical systems and a higher risk of electrical hazards. The neutral conductor is grounded at the service entrance, and all metal parts of the electrical system are bonded together. Lightning protection systems are often installed on commercial buildings to protect against lightning strikes. Surge protective devices are used to protect against voltage surges. Now consider an industrial facility. In an industrial facility, the grounding and bonding requirements are even more stringent than in a commercial building. This is because industrial facilities typically have very complex electrical systems and a high risk of electrical hazards. The neutral conductor is grounded at the service entrance, and all metal parts of the electrical system are bonded together. Lightning protection systems are often installed on industrial facilities to protect against lightning strikes. Surge protective devices are used to protect against voltage surges. In addition, industrial facilities often have equipped potential bonding systems to minimize the risk of electric shock in areas where people may come into contact with metal parts. The effectiveness of grounding and bonding depends on several factors, including the quality of the installation, the type of soil, and the frequency of lightning strikes. It's important to have a qualified electrician install and inspect your grounding and bonding system to ensure that it meets all applicable requirements. Regular maintenance and inspection of the grounding and bonding system are also essential to ensure its continued effectiveness. Grounding the neutral and bonding all metal parts of the electrical system is a critical safety measure. It helps to protect against electric shock, fire, and damage to equipment. It's important to understand the principles of grounding and bonding and to ensure that your electrical system is properly grounded and bonded. Remember to consult with a qualified electrician for any questions or concerns about grounding and bonding. Here's a summary of key takeaways. Grounding the neutral at the service provides a lower impedance path for lightning energy to flow to ground. Grounding is also important for fault clearing purposes. Even with proper grounding, lightning can still induce high voltages on phase conductors. Lightning protection systems are the best way to protect against lightning damage. Grounding and bonding are essential for electrical safety. The NEC provides detailed requirements for grounding and bonding. Regular maintenance and inspection of grounding and bonding systems are essential.